You have compiled a C++ program on Windows. You try to run that exact same executable on a Linux machine, and it fails immediately. It is not even close to working. Yet, you can compile a Java program on your Mac, zip up the resulting .jar file, send it to a colleague running Windows, and they can execute it without any recompilation. How is that even possible? This fundamental difference is Java's core superpower: write once, run anywhere, or WORA. It is a promise that changed software development forever, allowing applications to transcend operating system and hardware boundaries. Today, we are going to unravel exactly how Java delivers on that promise. By the end of this lesson, you will be able to clearly differentiate Java's WORA model from the traditional ahead-of-time compilation approach used by languages like C++. You will understand the distinct roles of Java source code, the intermediate bytecode, and the Java virtual machine, or JVM, in executing your programs. I will show you where Java's WORA promise holds perfectly, and critically, where it faces practical limitations you need to be aware of. Finally, we will look at some of the massive enterprise applications and ecosystems that are built entirely upon the JVM, demonstrating its pervasive influence in modern software. When I first encountered Java's WORA, I thought of it like a universal instruction manual. Imagine you buy a piece of furniture from IKEA. The instructions are pictorial, language agnostic. It does not matter if you are in Sweden, Japan, or the US. Any skilled builder can follow those same instructions to assemble the furniture, regardless of their specific tools or native language. In this analogy, your Java source code is the original design concept. The Java compiler, Java C, takes that source code and translates it into this universal instruction manual, which we call Java bytecode. This bytecode is stored in .class files. It is not native machine code for any specific CPU, but rather a set of instructions for an abstract machine. The Java virtual machine, or JVM, is our skilled builder. There is a specific JVM implementation for every major operating system and processor architecture combination. So, you have a JVM for Windows on x86, another for Linux on ARM, and so on. Each JVM knows how to read and execute that universal bytecode, translating it into the native operation specific to its underlying platform. This two-step process, compiling source to architecture-neutral bytecode, then running that bytecode on a platform-specific JVM, is the core mechanism behind write once, run anywhere. The bytecode itself is a compact, pre-verified intermediate representation, not interpreted directly from your original .java file. The JVM loads these .class files, verifies their structural integrity, and then executes them. Let me show you how this works with a simple example. We will write a classic Hello World program. I will announce the code, then we will walk through it line by line, and then I will show you the compilation and execution. Here is our Java source code. This line, public class Hello World, declares a public class named Hello World. Java requires that the file name matches the public class name, so this file must be named helloworld.java. Inside, public static void main, string array args, defines the entry point for our program. This is where execution begins. And finally, system.out.println hello world prints the string literal hello world to the standard output. This is a standard library call that interacts with the underlying operating system to display text on your console. To compile this, you open your terminal and type javac hello world.java. The javac command invokes the Java compiler. If there are no syntax errors, it produces a file named hello-world.class in the same directory. This .class file contains the bytecode, our universal instruction manual. To run it, you type java hello world. Notice you do not include the .class extension. The Java command invokes the Java virtual machine. The JVM loads hello-world.class, verifies it, and then executes the bytecode. When you run this, you get exactly this on screen. It prints hello world. The key here is that this hello-world.class file can now be taken to any machine with a compatible JVM installed, whether it is Windows, Linux, or macOS, and it will execute identically, producing the same output. Now, while WORA is a powerful promise, the reality is more nuanced than absolute perfection. This is the part most tutorials skip. For most server-side, headless applications, it holds almost perfectly. A Spring Boot application packaged into a FAT-JAR on your Mac will run unchanged in a Linux container in production, provided the JVM major version is compatible. However, you are going to run into situations where subtle differences emerge. Thread scheduling policies, for instance, differ between operating systems. The accuracy of system.nanotime open parenthesis close parenthesis, which you might use for high precision timing, can vary. file locking semantics diverge significantly between Windows and Unix-like systems. Even graphical user interface subsystems like AWT, Swing, or Java FX rely on native peers that can behave slightly differently. Another common misconception about Java is its startup time. Portability comes at a cost. The JVM performs a lot of work before your application reaches peak performance. It needs to load classes, verify their integrity, perform static initialization, and potentially interpret bytecode before it even considers optimizing it. This initial overhead is why Java applications traditionally felt slow to start. But here is where it gets interesting. After this warm-up period, the JVM employs a just-in-time, or JIT, compiler. The JIT dynamically converts frequently executed bytecode into highly optimized native machine code at runtime, leveraging runtime profiling that static compilers cannot see. This means that after your Java application has been running for a while, its performance can often rival or even surpass that of ahead-of-time compiled languages like C++. The JVM observes your code's actual execution patterns and optimizes hotspots aggressively. However, if startup time is absolutely critical, there are solutions like GraalVM Native Image. This technology allows you to compile your Java application ahead of time into a standalone native executable, completely bypassing the JVM's startup overhead. The trade-off is that it gives up some of the JVM's dynamic optimization capabilities, as the code is fixed at compile time. Because of this robust WORA model and the powerful JVM, Java's presence is pervasive across the industry. The Spring Boot ecosystem, for example, powers millions of microservices, often running on embedded web servers like Tomcat or Netty. Apache Kafka, the de facto standard for message brokering in distributed systems, is written in Java and exposes a Java API. Elasticsearch, the distributed search and analytics engine, runs on the JVM. Even the backbone of big data processing, Apache Hadoop and Apache Spark, are JVM-based. Android's core APIs are Java, though it uses its own runtime, ART, instead of the hotspot JVM. Financial trading systems, which demand microsecond latencies, often squeeze incredible performance out of the JVM using specialized libraries. Even the tools you use every day, like build tools such as Maven and Gradle, CI/CD servers like Jenkins, and popular IDEs like IntelliJ IDEA, are Java applications. So what have you learned today? First, you now understand that Java achieves write once, run anywhere by compiling source code into platform-agnostic bytecode, which is then executed by a platform-specific Java virtual machine. Second, you know that while WORA is incredibly powerful, it has practical nuances regarding OS-specific behaviors and initial startup costs. And third, you are now familiar with the critical roles of JIT compilation for runtime performance optimization and AOT compilation with tools like GraalVM for fast startup. You also know that Java is the foundation for a vast array of enterprise applications, from microservices to big data. Next time, we're going to dive deeper into the Java ecosystem, JVM, JDK, JRE to understand the full toolkit you will be working with.